This is the first of a series of videos on Chapter 3, Electricity, for Year 9 Science. This is Chapter 3.1, just a summary on the chapter from the textbook, the Good Science textbook, Year 9 and Year 10. So as I did in class, before I delve into the details of the different quantities of electricity, I always like to start from the beginning, the very bottom, and that's atoms. So an atom is a building block of matter. Okay, there's about 118 different types of atoms. These are called elements. So oxygen, gold, silver, copper, helium, and so on and so forth. They're elements, the different types of atoms. And all atoms, they've got three basic components, three smaller particles. And I like to use the acronym PEN: proton, electron, neutron. Protons have a positive charge, P for plus charge. Electrons have minus charge, and neutrons are neutral, they've got zero charge. So let's take a simple atom like helium. So helium has 2 protons and 2 neutrons. This is collectively called the atomic nucleus, and that lives at the center of the atom. And around the nucleus, you've got the electrons, much like planets orbiting the sun. So the sun is like the nucleus, and the planets are like the electrons orbiting the sun, the nucleus. Helium has 2 electrons. It's the second element on the periodic table, atomic number 2, so it's got 2 electrons and 2 protons. An atomic mass of 4, so you can see there's 4 particles in the nucleus, 2 protons and 2 neutrons. Now, in studies of electricity, the main subatomic particle we're interested in is the electron. It's a very special particle, this guy here, because it basically defines electricity. And here's where I define electricity. Electricity is the flow of electrons. That's our starting point, okay? Not interested in protons, not interested in neutrons, we're interested in electrons. So electricity flows through things called wires. These are like cylinders. Copper is typically used to make wires. Copper is highly conductive. Conductive means it can allow electricity to pass through with relative ease. Things like copper, things like silver even, gold. Metals typically. So copper is a conductor. It's a thermal and electrical conductor. That means it also conducts heat. It's good at spreading heat. Means conducts electricity. There'd be no point in using plastic, let's say, to make wires, because plastic is a poor conductor. It's an insulator. So in a wire, if you zoom into a wire, copper wire, it's made of copper atoms. So I'll draw it fatter, just to make things easy to see. I'm going to draw atomic nuclei, represented by a plus sign and a circle. Okay, because atomic nuclei have a net charge of plus. The total charge of an atomic nucleus is plus. Students still get this wrong till this day. It's a very simple concept. So let's take helium. Let me draw a seesaw. That's how I like to think of atoms. Helium has, up here, 2 protons and 2 electrons. So there's 2 protons and there's 2 electrons. My bad. 2 neutrons. Let's look at the atomic nucleus, the total charge. Let's work it out using a seesaw. Protons have charge. Neutrons don't have charge. They're neutral. So they don't contribute to the charge of an atom. Hence, the atomic nucleus has an overall positive charge. So you've got this is called a C. C of positive copper nuclei in this case. This is also known as metallic bonding, or the free electron model. Okay, there's different types of bonding we explored in chemistry: covalent bonding and ionic bonding. Metallic bonding, as the name suggests, only applies to metals like copper. And around this lattice, I should say, also known as a lattice, Lattice means regular arrangement. The positive nuclei are regularly arranged in like rows and columns. Amongst this lattice, you've got free electrons, and hence the term free electron model. Okay, I put minus signs here. The electrons are simply free to flow. That's what makes metals like copper great conductors, because the electrons can flow through a wire, let's say. Okay, so free electrons there, and they're moving, they're drifting in a particular direction, let's say in the right direction. And that's electricity. If you had an insulator, the electrons would be bound. They'd be stuck onto their nuclei. They wouldn't be able to move, and hence there'd be no electricity flowing. I should also mention that just a fancy way of saying free electrons, also delocalized electrons. Think of your local supermarkets. It's close to you, right? Delocal would mean it's far. So the electrons are far from their respective nuclei. Just think of like a kid and their parent. The nuclei are the parents. The kids are the nuclei, so they're pretty much free to go anywhere they want. Okay, the kids. Now we can get into the important quantities that define electricity. So this is something that all sparkies or electricians need to know. People who deal with electricity, electrical engineers, electronics engineers, physicists, anyone who works with electricity needs to know these next three quantities. Three important quantities, electrical quantities. Okay, for aviation fans as well out there, same thing. You need to know your electricity or physics to do aviation, study aircraft, to fly aircraft. So it's not just restricted to science, it's also applicable to other jobs, other careers. Let me start off with voltage. I'm sure you've heard voltage and power lines and all that. So voltage is basically a measure of, loosely speaking, it's the pushing force. It's the pushing force through a conductor. Let's keep it at that for now. Think of a hand. Okay, a hand that's pushing electrons along a wire. Okay, that hand is voltage. Right, think of a fridge. Right, to move a fridge, you need to apply a force, right? And think of you pushing the fridge as the voltage in this case, and the fridge is the electron. So it's a measure of pushing force. It's also known, here's where it gets a bit fancy, physics lingo, also known as potential difference. It's a simple concept. Think of temperature difference. I always tell my students, think of it this way. You're inside a room and there's someone outside the room. Let's say there's someone standing at the door. Someone standing at the door wants to work out the temperature difference between inside and outside the room. Person inside the room has a thermometer and measures 20 degrees Celsius. Someone outside the room measures on their thermometer, let's say 30 degrees Celsius. What would the temperature difference be? That would be quite straightforward to do. It's basically 30 degrees minus 20 degrees, which is 10 degrees. But I haven't defined the reference point. So reference point means, so let's take this as being, I should say, let's do an example here. Let's now use an electrical analogy. Suppose I have an electron sitting here initially, then it moves sometime later, let's say, 5 seconds later, to another position here. At this initial position, initial means the starting point, it experiences a potential difference of 5 volts. Okay, now voltage is measured in volts. Named after Alessandro Volta, famous Italian physicist who invented the battery. Symbol V. Okay, units are volts, symbol V. The more volts, the more pushing force. Okay, so let's say 100 volts versus 50 volts. 100 volts is going to do a lot more damage, right? A lot more impact. It's a bigger number. The bigger the number, the more voltage, and vice versa. So initially, let's say 5 volts is applied to it. 5 seconds later, it's at its final position, and the voltage is measured to be 10 volts. Okay, this is a hypothetical scenario. And I want to work out the potential difference, PD for short, yeah? What's the potential difference? Now, same as temperature, I would take the final voltage. So potential difference is basically the difference in potential energy between 2 points. potential. So energy is measured in joules, but for now we're looking at volts. So we'll get into the energy topic. We'll look at energy in detail, but for now it's just volts. Okay. So the final voltage minus the initial voltage. Final is 10 volts, minus the initial, which is 5 volts. 10 minus 5 is 5 volts. That's the potential difference. That's the difference in energy between the final and initial points. So that's potential difference. And voltage, to recap, is just a measure of the pushing force acting along a conductor on electrons, let's say. And voltage, I should mention, can also be detrimental, can also be nasty, unnecessary in a circuit. Suppose you have a battery and a light bulb. If there's too much volts, too much pushing force applied to the electrons, and they're flowing through a light bulb, the light bulb probably won't be able to cope with it, and it can actually fail or blow, and it will wreck the light bulb. It'll damage it. And batteries are a great source of voltage. They provide the pushing force in circuits. That's why your phones need a battery, right, to work. The battery provides the pushing force to push electrons through the wires in your phones. Laptops need batteries, watches, so on and so forth. Okay, so batteries are typically sources of voltage, of potential differences. That's voltage. Now on to current. Use a different color. Okay, I'm sure you've heard the word current before. Think of current in a river. Okay, and someone says there's a high current, it's probably best not to jump in the river. Okay, high current means there's lots of water flowing. Similarly, in a circuit, if there's lots of current, there's lots of charge flowing. So current is defined as the rate of movement or flow of charge. Okay, how much charge is flowing through a particular point in a circuit. Okay, in a wire, let's say. Charge can be plus or minus. Okay, it could be positive particles, positively charged, negatively charged negatively charged particles as well, like electrons. Not necessarily electrons only. Current has the units of amperes, named after Andre Ampere, a French mathematician and physicist who did a lot of work in electricity and magnetism. Amps, units, A for short. The more amps, the more current. So 100 amps versus 50 amps, 100 amps is going to be a lot more, right? Think of a river with high current versus a river with low current. The one with high current has a higher number of charge, higher number of current in this case. So it's simply how many electrons, let's say, are flowing through a wire conductor. Okay, so in this case, there's four electrons versus, let's say, 2 electrons. So this is a greater current here. I'll leave that there for current for now. It's very straightforward. Number 3, let's look at resistance. Resistance is something I'm sure you've heard of before. Think of resistance outside Parliament. Okay, an opposition basically. Resistance basically means opposition. So the opposition, we're not interested in Parliament in this case, we're interested in electricity. The opposition to current flow. Anything that opposes current in a circuit is resistance. It's resisting, it's preventing current flow. And it's actually a intrinsic, here's a fancy word for you. I want you to commit this to memory, it's a good word to know. Intrinsic property of any material. Okay, intrinsic means inherent. It's a specific property. It's an inside property. Think of it that way. It's a feature, characteristic of any material. So different materials have different resistance. You obviously want a material with low resistance. The less the resistance, the more the current. So less resistance, more current. Think of a river. Perfectly flowing river. If I add stones, lots and lots of stones over time, I'm going to eventually prevent the flow of water in the river. That's going to block the flow of water, the current. Same thing in a circuit. If I put obstacles in the circuit, if there's defects in the circuit, defects meaning obstructions or damage to the material, let's say, that's going to cause more resistance. And there's always going to be resistance in in a circuit in conductors because no conductor is perfect. As far as we know now, there's no perfect zero resistance conductor that operates at room temperature, I should say. You can make zero resistance materials at very cold temperatures, but you need really cold temperatures. But yeah, to find an ideal conductor with zero resistance, that'd be the holy grail of electronics. You can make a lot of money from that. But anyway, putting that aside, resistance is measured in ohms. It was named after George Ohm, German physicist and mathematician, who did lots of work on electricity and is also known as the Mozart of electricity. We'll look at him later on. Ohms, so they're the units. It's given, so omega is the symbol. Omega is a pair of legs. It's a Greek letter in the Greek alphabet, omega. The higher the resistance, the less current. So let's say you got 100 ohms versus 10 ohms. 100 ohms is less preferable. So that's it for 3.1. So to recap, voltage is the pushing force in a conductor, acting across a conductor, being applied to electrons, measured in volts. It's got units of volts. Current is the rate of movement of charge in a circuit. It's basically how many electrons, let's say, are moving along a conductor, measured in amps. And resistance is the opposition to the movement of charge, movement of current. It's measured in ohms.